This is the Math Map Book Club, where ordinary parents encourage one another to develop an extraordinary appreciation of math. We love what we know, and we struggle over the unfamiliar. Through weekly conversation and exploration among friends, we can begin to enjoy ideas that might seem difficult. Join our book club as we discuss how math helps us to know God and to make him known. I'm Lee Bortons. It's Wednesday, August 30th, 2023. Welcome to the Math Map Book Club, where Kirsty Gilpin and I spend each week discussing a different concept from math from our soon-to-be released curriculum for families with students in classroom conversations called the Math Map. We spent a lot of time in the last few years exploring the difficulties of math education, and we found that there's many reasons people don't like math or find it difficult, but if they can be identified, they can be overcome. And so we're here to help you do that on this show each week. Welcome back from last spring. I know I missed last week's episode where Kirsty did a great job leading it. And I just want to remind people that as we get closer to the launch of the Math Maps release in early 2024, to remind people they can come on here and ask us questions. That's what we're here for, to make sure that we're accessible to you. So with that, thanks, Kirsty. What do we have today?
So today we are on lesson 17, intersected shapes, and the orientation of the artwork meant I could fit all three pieces on, but I know we don't really have time to talk about all three pieces of our cover. So I'm just going to go with speaker's prerogative and say that I love this piece of artwork by Kandinsky. I am not normally an fan of modern art, but I really like his work and this piece in particular. So let's start it out by just seeing when you guys look at this, what do you see? What do you like? And why do you think we chose this as the cover for Intersected Shapes?
I definitely see oils.
I was going to say, I just see a lot of geometry here.
I see shading.
When you say geometry, what do you mean?
Well, when you think about all the basic shapes of geometry with triangles and circles, there's maybe squares, but yeah, there are some squares over on the right side. And then some irregular, quadrilaterals and things like that. Lots of intersected lines. So it feels like one of those things that you see on social media when they say, how many circles do you see in this? And it tells you something about yourself.
I think if you look at the top right with the 5 stripes, it reminds me of music. Page of music, but I know it also bends around to the left. So obviously it was supposed to indicate something else, but that was a pattern that jumped out at me. And when I looked at the tic-tac-toe almost with those squares and how it's not quite tic-tac-toe, it reminded me of my grandbabies. I am sure that would stand out immediately to one of them because we play what we call modified tic-tac-toe, where they can take straws or forks and knives at the restaurant or a piece of paper, whatever they want, draw as many boxes as they want that are big. And then we use coffee cups or those little cups of milk, or we use beans or whatever. And we make up our own tic-tac-toe games of all size boards. And so when I saw that, I thought that's what they would think of when they saw it.
I think it's interesting how everything is familiar and yet together it's very unfamiliar.
Yeah, is that supposed to be a ship on the left?
I think that's part of modern art. You can see what you see, and I may not see what you're seeing. I see skyscrapers.
I see the sun shining up there in the left corner.
Or if you're a Star Wars fan, 2 suns.
I was gonna say, there's a sun and it's like a black sun and then multiple moons of different colors because the shading around them, all of them have kind of an aura around them.
Right.
I like all the semicircles. They look like bubbles trying to rise out of the page.
I always think this is a really accessible piece of art for our students when we're talking about math, because we can pull out all those shapes and we can talk about how they're intersected and there's different shapes and there's different lines. So I always feel like it's very accessible, but at the same time, we can interpret it however we want to. I always just think it's pretty. Maybe it's the fact that he used so much pink that makes me happy.
It makes me want to go organize the Lego box. Because I can't push that around the piece.
That's true. Well, as Lee knows, my son has a lot of Lego, which historically has always been sorted by color. And lately he has been researching different storage opportunities so that it can be arranged both by color and by type of piece. So lots of Lego sorting that we could do. All right, well, let's go ahead and look at our next slide. Sorry. As we look at a little piece of our math map. And so remember, each week we're trying to talk about the math map, right? That's our goal, is to recognize that there's a map to mathematics education. And that by looking at these topics dimensionally every year and moving through our domains, students can move from square one to square 390, building up their familiarity with the mathematics grammar, and along the way developing understanding and hopefully beginning to at least approach the rhetorical stage in preparation for going on to deeper studies in the quadrivium. So we've been in two dimensions for quite a while. And as we look at this and we think about the language and the order of mathematics, one of the things I wanted to point out is that this idea of review through repetition. So we have yearly repetition, but we also have the repetition of ideas and patterns. One of the ways that shows up is in the dimensions, right? That as we see addition in 1D, and then we use addition in 2D and in 3D, or we look at lines in 1D and then 2D and 3D, we're reviewing these ideas and we're going a little bit deeper each time as we expand what we're looking at through that dimensional lens. But also, if you look here within 2D, we had straight lines, intersected lines, and curved lines. Then in polygons, we had shapes that have straight sides, circles that had curved sides. And then constructions and assessment, we're going to kind of hold those a little bit out of that pattern. But at 16, we jump back into triangles and circles and intersected shapes, where we have that intersection of the curved and the straight, right? And so we're going to continually be looking at these ideas as we look at them, right, over and over again. We're going to see that there's a built-in repetition and review in the math map.
Christy,
And
I
so-
want to add that, can you go back? Because I just saw something else we even talked about, maybe did last week. But the first 3, 9, 10, 11 are open shapes, and then 12, 13 are closed shapes. And then 16, 17, and 18, we start mingling open and closed together and even moving them around with the transformations.
And that artwork you showed us had all of those things: open, close, curves. Yeah.
So many patterns, right? And so we're beginning to become pattern finders. That's what mathematicians are, pattern finders. And so the joy, right, of finding those patterns. So not spending a lot of time here, but pointing out we are still in 2D. We're talking about intersected spaces this week. And let us jump into doing that. Great. So while I'm waiting for this to back up, I once had the opportunity to fly a P3. And when I say fly, I mean sit in the pilot seat and fly it. I did not take off or land or any part of it that was complicated, just for clarification. Before that, I had only had the opportunity to fly a Cessna, which is a very small plane. When you fly a small plane, it is very responsive, right? You push the yoke forward and the plane goes down. You push the yoke back and the plane goes up. And in the P3, it's a much bigger plane and much slower. And so as each of us, we were high school students, had the opportunity, you would push it forward and it wouldn't do anything. And so you'd think, oh, I need to go a little bit more. And you'd push it forward. And then all of a sudden you die. And you'd start to pull it back and it wouldn't do anything. And you'd pull it back even more. And then you'd fly up. And so the whole flight was doing this the entire time because we weren't patient enough to see the results, all right, of our first correction, just like I wasn't patient enough there. And sometimes we're like that with our students, aren't we? That we aren't patient enough. We give them a little nudge and they don't do what we want right away. And so we push them harder and then we oftentimes don't get the response we're looking for. So just PowerPoint there giving us all a little reminder that sometimes we just need to be a little bit patient before we overreact. So as we talk about intersected shapes, I thought we'd take a minute and talk about the fact that this is the math map as a curriculum seeks to present math in an integrated way, right? We're looking at math through dimensions, but we're building a whole, right? We are not segmenting math up. We're trying to build a whole so that we see the math map, right? Not just our curriculum map, but how do the pieces of math fit together? And I sent Leah an article, and it was short article, but somebody asked a PhD professor at some university, right, about how math fit together. And he was like, I don't know. I don't think anybody knows, right? Because he had become so specialized. And so one of our goals is to help parents, students, families see math as this integrated whole, right? That's pointing us towards God, not as fragmented pieces. They're just like classical education, right? We're trying to bring this holistic idea of education back and get away from those fragmented pieces. And intersected shapes is a lesson that's a great opportunity to do that, because we're going to look at these intersections both from a geometric standpoint, looking at the figures, and we can also look at them from an algebraic standpoint, where we talk about where their location is and identifying it. So let's take a look. The back chart there has some pictures of some things that might be intersected. Then I've got a piece of another chart overlaid on top of that that gives you some pictures of how things can intersect. So go ahead and look at those images on the screen and what kind of figures can intersect. And Lee sort of alluded to this in Jana when you talked about the kinds of figures that were on Kandinsky's painting.
Are there any figures that can't intersect?
That's a good question.
That is a good question. So can open figures intersect?
Yes.
Do we have to actually ask if they're in the same plane or not? Or if they're the same
that is-
dimension or not?
Well, if we're only in 2 dimensions, they have to be, right?
Yes.
Unless they're on parallel planes, and then that gets interesting.
Or parallel lines even on
Right.
one plane.
So if things are not in the same space, there you go. There's a way we could say what doesn't intersect, right? If they're not in the same space, then they're not. When we get to 3D, we may not in this series talk about it, but the idea of skew lines are introduced because they don't intersect, but they're not parallel, right? So something like this, these two lines, you know, going this way and going this way are skew because they're not in the same plane. Right, so they cannot intersect. So that's a great observation.
Parallel lines can't intersect.
Okay.
Well, like I'm looking at your polygons in the middle with the red and the blue triangle, and even though if you identified them as purely as lines, the lines can intersect, but as shapes, they're not intersecting. Am I saying that right? In other words, there's
So
yeah.
So if they were on a grid, they do not intersect, but you could take them and put them on top of each other to intersect.
Mhm.
So it's weird because like, you know, except with the exception of saying parallel lines, those we know do not intersect by definition. Any other lines could possibly intersect. It's not that they can't. So yeah, it's interesting. So like the polygons, the way they are drawn, they do not intersect. Can they? Yes, we could fold the paper and make them intersect. But if they were on a grid or we had a coordinate plane that they had specific locations, then no, they could not intersect because they are on specific, they have their addresses.
So we're getting a lot more specific there, but we've said that lines can intersect, and actually if they're coplanar lines and they're not parallel, then they have to intersect. Even if we don't see it, if they're lines, they're infinite, and so if they're not parallel, they have to intersect. But then we can also look at curved lines. And so we see an example there of curved lines. We don't really describe them as parallel, but that's kind of the sense of what they are, right? They're sort of parallel, so they're not intersecting, but we certainly see that curved lines can intersect. And we've got polygons, straight-sided figures, and we've got curved figures, our circles, right, that we see can. So let's look at how these figures, right, these figures that can intersect with one another, how can they? How many points can a straight line intersect another straight line?
One.
Or infinite.
Or one or infinite, yeah.
One or infinite, right? They're either 1 point or they're essentially the same line. If I have two curved lines,
Depends on how many curves.
Right.
okay,
So in the case we have here, we can see where it's many points, it's 2 specific points, and it's maybe 3 specific points. So there's a variety of them based on the curves.
depending on how they intersect, it can be a lot of discrete points, or it may be some discrete points and some sort of infinite points, right? Some portions that are coincident. And then similarly, right, with our polygons and our circles, we may again have finite points of intersection, or we may have infinite points of intersection. Right? So when we have different shapes, it becomes kind of interesting how many different ways they can intersect.
Could I ask a quick question of just definition? I'm not familiar with the infinite consistent, so would we categorize that as an intersection? I
Yes.
just thought of that. So that would be classified as that. Okay, thank you. That's helpful.
I like the way you drew the last column with the purple lines. You have the red and the blue, and so that just gives you an image of they're sitting on top of each other. I didn't know how you would draw that to make it clear that there were.
It's hard, Jana. It's hard to sometimes right show these ideas. So
With the little guys, we were trying to figure out, like, could we do tomato sauce on a pizza crust? Like, what could we do for them to see it's the same, but it's not? And eventually
still
just
be
kind of
layers.
realized it's, no matter how thin it is, it gets a new dimension to it and it changes the definition. So,
Right. Well, I like this. The red and blue in the first two columns just sets you up to realize, okay, something's different here. Even if you're a little kid and you haven't learned primary and secondary colors yet, well, this is a good time to learn that. Yeah, that's good. Genius.
So now everybody wanted to talk about, right, when we're in the coordinate plane and having addresses and locations. So how, if we're in 2D, how many coordinates describe a mathematical location?
2.
2, right? So that's what we oftentimes call them our X and Y. They don't have to be X and Y, right? But those are our horizontal or our abscissa, and our vertical, which is our ordinate. So those are our big fancy names that we like to use. Right, we like to use X and Y. We're familiar with those. But when we use the math terms of abscissa and ordinate, it actually gives us a little bit more breadth to realize that we can use any variable there. So we have 2 coordinates. So now knowing that every point has 2 coordinates, and sometimes I might describe a rule that gives me that curve or that line, or I may just have the points of my polygons or a formula for a circle. So there's lots of ways that I can describe these shapes in the plane. Where they intersect, what has to be true about the location of the points at the intersection?
their X and Y have to be the same.
Exactly, right? So if I have 2 lines that intersect, that X and Y, those 2 coordinates have to be the same for both of those lines. They have to solve both of those lines. So there's a math term that we often hear, that when we say this point solves the equation, what it means is if my line is y equals x plus 1, right? And then I say that 4, 3 is, or 3, 4 is a solution. It means that if I substitute 3 for x and I substitute 4 for y, it makes the equation true, right? So that coordinate makes that equation true. And so if I have a point of intersection, it has to make both equations true at the same time.
I think we don't use practical examples enough. Like we'll do y equals mx plus b, and it'll be 2 different equations, and we're trying to explain to a child that they have to have that same x and y when they intersect, but we never say to them, you know, like the crossroads outside of our neighborhood, that if you get Grant Street with 211, where they intersect, both of them have the exact same GPS, right? The exact same location or the exact same address. We can show, almost all of math can be seen concretely, but at the algebraic levels, we tend to forget that.
Or just latitude and longitude. That point has to be, right? It's on both of those lines, that intersection. Yeah, so when we talk about location, when we're talking about coordinates, talking about physical, practical location is a great way to help students to put some real things to that, right? But we could talk about other intersections, right? When we think about sets, right? If you wanted to go back to here, we're talking about intersected shapes and locations, but this is a great opportunity to go back and think about the intersection of sets. So if I said I have a set of 5 ice cream cones, right? And I have a set of 5 people, right? And I said, okay, there's 5 and 5, right? Is there an intersection there where one person might get the ice cream cone that they like? That would be a happy intersection, right?
Or
maybe
not happy because they didn't get what they liked.
I was gonna say, or very happy if everybody gets what they like.
So is that just how you would use that example with a kid, that there's 4 of us and we're all getting different ice creams? And your set is making you happy because you picked it, but what if I'd steal it out of your hand? Now do I have the same set but a different order? Like, how do you talk about that?
Well, there's different ways that we could talk about it, right? Even if you just talked about the numbers, what if I only had 4 ice creams in one set and I had 5 kids in the other set? And now there's not a one-to-one correspondence between the two. What happens?
So that's a case where there's not a complete number of intersections.
Right? Somebody gets left out. Right. Well, I'm going to go to our next slide, which is just reminding everybody of the Math Map launch that coming in the spring of 2024. And I think we're looking at sort of mid to late spring, just so you're not all marking your calendars for March 21st. We will have, the plan is for 2 new sets of flashcards to be available, which is very exciting. And the Challenge A complex domain, the complete curriculum, will be available. So we're excited about that. We're currently working hard to gear up for how we equip all the Challenge A tutors across the country to implement the Math Map in their classrooms. So we're very excited about that. And then for everybody else, for parents and for those families who are eager to get started, the current plan is to release the digits. The naturals, I believe, will continue to be available, and the fractions level, those will all be available digitally, which means not the complete curriculum, but the lesson pages. So those will be available on CC Connected. And along with that, we will begin releasing access to the companion, the beta version of the companion. I want to be very clear that it's a multi-year project to get the companion up and going, but we will be releasing digital access to that in the late spring also. So it's coming ever closer.
Can I ask a quick question?
Yes.
So if you don't have a Challenge A student next year, are you allowed to purchase the curriculum? I did start my son in A this year because it just felt like the right thing to do, but can I do the Challenge A curriculum with him at home when he's in Challenge B?
Yes.
Good.
It will be for sale on ccbooks.com. And if you have a credit card, you can get it.
Okay. Good.
The only thing that we would strongly recommend is that if you do not have a child in challenge, do not start the complex level.
Yeah.
Right. So if your child is enrolled in challenge and you're like, hey, I want to use the Math Map, even though we're not in A, we're in B or 1, we're going to start with complex. That's great. But we're just really encouraging families who have students who are not yet in challenge to wait on the complex domain and instead use one of those other levels that we're releasing digitally.
Okay. Sounds good.
And if you're planning to use the complex next year, I would strongly encourage you to get those natural pages out and be working through those this year. We have consistently heard from pilot families that the families who did the naturals in advance of starting the complex level are finding it a much gentler entree into the curriculum. They're sticking with it. They're having a much higher degree of success. They're really hitting the ground running. So if you are anticipating doing the complex next year, I cannot stress enough working through the naturals this year.
And I saw both Jill and Angela are on the call. Would you agree with what Kirsty just said? Then give a thumbs up. Yeah. their children have been in it for a while, and it's your older challenged children also, right?
Yes, my oldest son, who just graduated this spring, just recently, he did math map over and over and over at the complex level. He was in an upper challenge when the pilot started, and so he, after a while, we quit what we were doing and had him join us, and he kept doing it repeatedly along with the Understanding Mathematics booklet, and that's all he did. And his year-end testing at graduation showed superior and very superior in all mathematics levels of his testing.
And the
Thanks,
same
Jill.
thing happened with my family. We had repetition of the same level over and over again. And when my eldest graduated high school, after ACTs, pre and post math map, there was a significant change in her scores.
Thank you. Well done, mothers.
Yes. All right. So let's go ahead and look at some examples from our naturals level. And so this is a great, if you haven't taken a look at that naturals level yet, this is a great opportunity to see what we ask those youngest students to do in terms of just building their grammar without having to demonstrate understanding. So, Amy, you were asking a question on the other chart, right? Where that chart sets up as our reference material. Here's an example of where we're going to pull that out for your youngest students. So what they would be doing is tracing. But Jill, would you read that as if you were reading it to your child while they're tracing it?
I would say these shapes are inconsistent. And then I would have them trace that word and see, depending on their reading, whether they would read it or spell it or those things. Then I would say they never touch each other and therefore have no solution. And I'd ask them, when you traced, did it touch? It should not touch. Some of them are going to be easier to not touch than other. The curved shape, they're going to have to be careful. They're going to, maybe we would draw the lines first and the circle and then say, now this one, is it supposed to touch? If they're really young, you'd lead them through on a simple level and they'd say, no, it's not supposed to touch. I'd say, okay, so we're not going to touch that line. We might need to use something erasable until we get it where it doesn't touch. You want me to keep going or just that?
Well, so from that, what do you think inconsistent means?
Right.
They don't touch.
Hopefully they would say they don't touch, right? Because it just says inconsistent and said no solution, but it didn't say they don't touch. So hopefully the conversation we had would help them discover that.
Great. So how about, would anybody like to talk us through the middle one?
Well, you could say, so these shapes have a consistent solution. So trace those lines. So what do you think consistent means? And then you can have them trace the second part. They intersect at one point.
Now, our students may not have any idea what inconsistent and consistent means, right? But as moms, what do you think inconsistent means?
No intersection.
There's no intersection, right? That they don't ever intersect, right? So what do we think consistent means?
Intersection.
That they do intersect, right?
And they may not know what that word intersect means either. And I always
That's
like to, I'm kind of a word nerd, but I like to look, so what's inter and what's sect? It's the origin, depending on how old your kid is. I think that's kind of fun to do.
I think at our house, this would definitely turn into a little devotion about when our expectations are met or not met? And do we think that we are consistent with making our bed in the morning or inconsistent with making our bed in the morning?
But I would be tempted to think that consistent would mean that they always line up, like that's,
Mm,
and that's a different word yet. That's, what was that, dependent? Was that the word?
Dependent or coincident.
mhm.
I'm curious why that is. Don't you agree that consistent makes it sound like it's gonna continually line up? But
Yeah. That's because you're looking at the geometry. The words start to make more sense when you look at the algebra. But for now, that's a great discussion with your children. That's a good math question. Would you have called it something else?
Or talk about what, right, said Jill, when you said that, if I talk about things being inconsistent, right, not mathematically, right? When I say these two things are inconsistent, what do I mean?
The goal was not met.
Okay,
There
so a
was-
goal wasn't met.
It did not touch what I expected, and what happened did not happen.
I think we also sometimes use inconsistency to mean sometimes with the goal is met and sometimes it's not.
It can be sometimes and not others. And
Right.
that's inconsistent.
In normal, like everyday language.
Mhm.
I think of oil and water. Right, sort of like a chemistry example there. They're inconsistent with one another. Do they really mix?
Not completely.
no, but they touch.
They touch, right? But they don't, there's no point that is both water and oil,
Right.
Unless
right?
you have a binder. Sorry.
No.
But for
Yeah.
a kid's example, right? When we think of things, like sleeping late in the morning is inconsistent with being the early bird that gets the worm, right? That when we use those words, we're usually saying these two ideas don't go together.
Mm.
I think saying it like that, where this idea is inconsistent with this, or this behavior is inconsistent with this result, is a great way to introduce some vocabulary that will be coming their way, that they'll hear. They'll hear it in books, they'll hear it in life, and for them to hear it more than one way and understand the difference is a great conversation. And it ties to math.
Okay, so back to the word nerd. The inconsistent could be it's not with it, they are not with. Consistent is with, con. So it's that Latin con is with. So not with, they never are with each other. They are never holding hands. They are never together.
We know.
So we can have a great, we could probably continue on, right? Because this is a great conversation where we're integrating geometry. We're looking at it in a coordinate plane. So we're looking at it from an algebraic standpoint, even though we're not doing any algebra, we're not doing any manipulation of variables, but we're seeing it in an algebraic content or circumstance. We're now talking about what do these words mean? How do these integrate with other things? Right? Right. That even from just looking at the naturals material, the material that was designed for 5 and 6 year olds, right? We can take and learn so much from this. So the bottom picture is also from the naturals curriculum. It maybe looks like it's a little bit more, but let's talk about what we see here. When we look at that, what kind of shapes are intersecting in this image?
Well, I know they're an ellipse and a parabola, but a child might say curves.
Lines, yeah.
They might even say circle.
Full
Oval, yeah.
egg shape.
Mhm.
So it's an opportunity when we start talking about the shapes to be able to also talk about exactly what their proper names are. Right? That it looks like a circle because is it closed or open?
Closed.
It's closed, but it's not quite a circle, right? So we could talk about that. So that shape is a closed curve. What are the other two curves?
Open.
Open curves, right? So we can talk about open and closed. Is this based off of what we just looked at above about consistent and inconsistent? Is this system of shapes or of equations, is it consistent or inconsistent?
Are you
Consistent
talking,
at
I would say
multiple points.
Both. I would say both.
Yeah,
talking about, are
cons-
the parabolas consistent, or are the three shapes like, are all three shapes being included in that question?
That's a great point. So here you go. Mea culpa. I will see, this is me just barreling through when I put this together. I didn't even actually read that they were parabolas. I just looked at that and I said, oh, hyperbolas. One hyperbola and all right, and an ellipse. So if it's one hyperbola and an ellipse, it's a consistent system.
So what is a hyperbola? What's the definition?
So, oh, you're asking me now, like
It's x squared over a squared minus y squared over b squared equals 1.
So
That's the algebra.
there are 4 conic sections. There's a circle, and that circle elongates or squishes into an ellipse.
Okay, so can I just ask it simply? Is this a picture of a hyperbola?
Yes.
Yes. Well,
Okay.
the two pieces together are a hyperbola. So a parabola just has one curve, where a hyperbola has 2 curves.
The two. And because they're symmetrical, we know that they are a hyperbola, not 2 independent parabolas.
Well, it could be either one. And had I actually read what was on that, so there is a classic mom fail, right? That we don't always like to read. We just like to look at the picture and assume that we know.
And then just so you guys know, we try very hard on all the grade levels, like if it's an ambiguous image, to give a clue on the page so you know which one you're supposed to be picking. So once again, the kids need to read too. And Kirsty, that's making me think I want to go back and revisit that page and see if there's something I can do to make it less ambiguous.
And notice we're not asking the kids to determine if it's consistent or not. That's just me challenging all of us, myself included, because I didn't read it. But that's one of the things, and we talk about the math map, and we keep coming back to how important it is to read first, right? Read the instructions, read the information that we're given, and not just jump into completing a calculation. And so that's where I failed today. Very
You
public.
didn't fail. You did the same thing we all do. But we're out of time. Do you have another slide? I want to make sure we get to all your points.
So that's really it. Just talking about that. And then next week, September the 6th, we will be talking about transformations and wrapping up 2D.
And come back and challenge us with those words, because it really will help us do a better job. Thank you.
Thank you.
Thank you.
Thank you.
Bye.